relative to the vertical and connected by two threads is suspended vertically and then released. Compared to free fall, the chain falls faster when it is dropped onto a horizontal surface. Explain the phenomenon and investigate how the relevant parameters affect the motion. We'll concentrate on the wooden blocks inclined, so all of the chains will be made out of wood, vertically suspended, free fall, horizontal. And the one falling on the horizontal surface will be faster than the free falling chain. Here we can see the photographic results that we got of the phenomenon itself. As we can see in the picture, on the right the chain is falling on a raised surface on a table, and we can see the difference in height in the LED trace, also the length of the LED trace, which gives us a higher speed than the one on the left, which is free fall. Now for some basic theory explaining this phenomena. Here on the upper picture we have a rod that is in the moment of touching the ground itself, so its velocity is v. On the second picture we have it after some time t when it starts rotating around point A. We can see the forces that are acting on it, and the speed v1 is bigger than the speed v. Also for the angles that are smaller than 25 degrees, we were looking at all of the collisions like plastic, so there are no elastic collisions. Here we can see an upgraded version where we have the rest of the chain on top. The same thing, on the first picture we see the chain itself in the moment of the contact with the ground. On the second picture we can see it after some time t, when the first rod started rotating. We can see that its speed is faster than the speed on the previous picture, and we can see that we have the force T, which pulls the rest of the chain down faster, and so the chain will get faster acceleration than G. And that will conclude our basic theory explanation. Now for the experimental procedure, we will be measuring time intervals for different bars needed to pass between the sensors, the height of the raised surface, and we'll be taking, as we saw previously, 120 FPS videos of chains. This is the first method we opted to use, but the camera was too slow to give any conclusive results. We will be measuring with Euler laser gates connected to a microcontroller which works at 10 kHz, and as previously mentioned, 120 frames per second camera. Here's how the basic setup works. The black bar on the bottom is the raised surface itself. The red dots are our lasers. Of course, the light wouldn't be seen, but we just wanted to have the presentation of it. They were fixed to a wall, and we have a chain, which construction we can see on the picture, and which will be further explained later in the work. These are the pictures of the equipment. For the photographic results, as we can see on the first picture, we have a mechanism for dropping both chains at the same time. It consists of a non-moving part, which is all of the wood color parts and the pins in the center, and the moving part, which is the red rod with the black pins, on which the chains themselves hang. On the pictures in the middle, we can see the setup itself, and on the right we can see the LED views to show the phenomenon itself with the photographic results, because the camera wasn't fast enough to capture the chain themselves. Now, for the chains themselves, we can see the geometry of them. We were using 12 by 12 cross-section, square cross-section rods that were, whose length was 30 millimeters, and this is what we define as the angle of the ladder, as we can see in the picture here. For all of the chains, a wooden mold was used to make the most accurate chains possible. Now experiments. All the experiments were repeated 3 times. The errors come from imperfect chains, because we could, even though we had a mold, the chains can never be made exactly the same, just because of the materials are not perfect. Slight string obligations, which also is in the imperfect chains. Speed of the microcontroller, as we said, it works at 10 kilohertz. And the position of the sensor, how well precisely placed. For the freefall method, for the laser method, we used same chain, so we get more relevant results. And of course, for the photographic method, as we've shown, we used two different chains, so we can compare them one to another. All of the graphs will represent speed needed to go between the sensors with respect to the number of bars. These are some of the parameters that we'll be talking about. These are mass of the bars, angle between bars, number of bars, and stiffness of the surface itself. Here is the first graph we got. This is the free-fall graph. The blue line we can see is the theory prediction of the free-falling chain itself for the time. And we can see the different chains we have made for 5 degrees, 15 degrees, and 20 degrees. What these graphs shows us is that the chains were made consistent because we watched that we measured all of the speeds of the chains themselves, intervened with the lasers at the half point because that's what we could control, and we kept that distance the same. And this proves that the results are pretty consistent for all of the chains, so we can later compare them to one another for different measurements. This is the formula that we use to predict the theory curve, as we have shown in the previous graph. The age 110 millimeters and age 60 millimeters are from the picture. Here, those are this measurement, this measurement, and this measurement. So essentially, we are looking at the speed at this point, the average speed between these two sensors, and that's and we're measuring the time interval that it takes. Now for the rest of the graphs, this time needed to pass between the sensors with respect to the number of rods for different surfaces. By different surfaces, we tried using different stiffnesses of the surface, the compression ratio, so we could see if that has an effect. As we can see in the bigger graph here, in the end, it has an effect, but a very small effect, small enough so that we can't really make a conclusion for the range of the parameters we have tested. But we think that with more extreme surfaces themselves, we would get some more consistent, better results. Here we can see the chain for different angles. Here we already have some pretty better results. As we can see here, the chain with the highest, with the biggest angle has the lowest time needed to pass between the sensors, and by that the highest speed. And we can see that it's just perfect. This is for different masses. I just want to note that we didn't use different bars, but we tried to weigh the ones down. We weighed them by adding weights to the center of the rods themselves and tried to see if that would have an effect. As we can see in the picture, we didn't get any conclusive results from this. Now, the speed results, as we previously mentioned, these are all of the average speeds between the sensors. We can see here the comparison of the free-fall chain, 5-degree chain, 15-degree chain, and 20-degree chain. Here we can see for different surfaces. The dark green ones are the same in all of the graphs. And here we can see for different masses. As you can see, the angle has the biggest impact on the chains. Now, for one more parameter that we mentioned in the beginning, when it comes to the number of rods themselves in a chain, it's self-explanatory. The more, as you can see in the graphs, the more rods we have, the greater the effect will be, because we get that effect while there is a collision with the ground itself with one rod. So the more rods we have, the more of that effect will be shown in our results. Now we come to the discussions and conclusions. We demonstrated the phenomenon and got some interesting results and tested some of the parameters. Our experiments show us that with the increase of the angle, the speed increases. We speculate that at a certain angle, the chain will start slowing down again, just because the impacts themselves won't be plastic anymore, but we will get some elasticity and there will be a lot of bouncing. So this is for the range that we used, this is the results we got. The results we got shows that the stiffness of the surface slightly changes the speed, but not by much in the area we tested. The length of the rod is another parameter which should be further investigated, but to test that parameter, we would have to use different rods that have different densities, but we would also like to have the same stiffness, so the bounciness, if I can call it that, would be the same as for the rods we have used. And with an increase of mass, we get a slight increase in speed. These are the references we have used. Thank you for your attention.
Please, could you open slide number 4?
Of course.
Am I right that velocity in the first case is less than in second?
I'm sorry,
Yeah, I mean the velocity of the center of the mass.
can you repeat the question, please?
V is more than V1 or less?
Less. V1 is the moment after the impact, so it rotates.
Okay, discuss later. Okay, please put your open slide number 13.
Okay. Here.
Where from this?
We use the equation, the normal equation for the accelerated movement. We can discuss that later in the discussion. It's the S equals GT squared divided by 2.
Excuse me, what happens if the angle between horizontal line and our stick will equal to 0?
If we have this
yes.
arrow, there will be no effect. We wanted to test that, but it is pretty hard to get them perfectly parallel. So we will see some effect if we try to construct the
So let's go. Yeah, get it. Have you considered last references?
Yes, we have.
So, and what is your personal contribution?
We use references more as the guidelines than for the work itself.
And okay, previous slide, please.
Okay.
And number. And could you open slide number two? Yeah, before. That's enough.
Right, 3 minutes. Okay. Can someone please write the attendance name on the board?
And may I start? And good morning, dear colleagues. My name is Budantsev, and I'm presenting the team of Russia with the opposition of the problem number 6, fast chain. And firstly, I will remind you the crucial point of the problem statement. Next slide, please. We have to investigate how the relevant parameters affect on the motion of the chain with the inclined sticks and explain this phenomenon. Next slide. And let's move on to the review of the report. First of all, we got the external setup, and I think this the setup has a very good quality. So it's the good point. However, I'm not sure about accuracy of the tracking. We didn't hear about something. So let's move on to the qualitative explanation. I disagree with this explanation because how the velocity in the second case, when we have a collision, is more than in the first case. Where is the reason for that? we didn't hear an explanation of this. So and what kind what the influence of the kind of interaction? Is it so? Is it absolutely elastic or inelastic? And then where the dependence of the angle on the angle. So the reporter in the specifying question said that if we have angle equal to 0, we have there is no effect. However, where the dependence of the angle in the formula, we didn't see it. And also for the experiments, we have spectrograms, and we didn't see any experimental point. So where the theory and where is the experiment, it wasn't clear. So, and then what the dependencies, however, considered not all relevant parameters, I think. And next slide, about theory, I think that theory is wrong, because we have dependencies only on the height, in theory, and the coefficient k, and where the, for example, mass, where the angle, or something like this. So, and for example, where is the is it relevant the fixing point of the this thread? So if we have these sticks, and in the first case we will fix our thread in these points, and in second case in these points, is it relevant or not? So, and let's move on to the second slide, to the next slide, excuse me. And I think the strong point of the report was the quite good quality of experiment, and from the weak points, I think the theoretical model wasn't right, and next slide. And also thread is absolutely neglected. I mean the coefficient of elasticity, yeah, and the collision character. Also, I think that a reporter considered not all the parameters that affect on this motion. And as a summary, I want to say that problem wasn't solved, and let's move on to the discussion. I will spend a little more time for the points. And the first question is why? Please, could you open slide number 4? And just explain me. Could you open slide number 4? And please, can you explain?
I would like to agree with you and accept that I made a mistake when doing the theory.
So, is it equal or not? Or
it's not equal.
Why?
It's less because of the impact itself.
So, however, the normal force acts on this point, and it means that this force acts on center of the mass too. So
yes, I understand that. It was honest mistake that they made.
What?
It was a mistake that they made. I completely understand. Thank you for.
Okay, so let's move on to the next question about. So what happens during after the collision with this point?
It starts rotating. We looked at the collision as I previously mentioned. That the collisions are complete with plastic, so this point won't move for the lower angles that we have tested, and it will just start rotating.
Just start to rotate. So,
yes.
And can you say something about the vertical projection of this velocity? Is it more than in this case, before a collision?
Yes, it would be more because to start rotating like this, it would be twice this.
Twice?
If we look for
I disagree.
Okay, and what's your opinion on that?
I'm not sure about that. It would be twice. However, so let's move on further. So, and however, in experiment, so your theoretical model was based on assumption that this point doesn't move. Am I right?
Yes.
However, in the experiment, we see that this point will bounce.
Yes, it will bounce, but
Is it
for the
important?
theory, yes, of course it is important. It will bounce when we test, but as just an explanation, we use that it won't bounce as the collisions are plastic, and it won't bounce, if I can say it like that, a lot for some lower angles.
Okay, yeah, got you. And okay, you said that you said that you agree with me that this velocity is approximately equal. However, how you can explain a good agreement theory and experiment if you have a mistake in theory?
We haven't made a theoretical model which would predict the speeds we measured. This is just the explanation of the phenomenon itself and how we think it works.
Okay, so let's move on to the your theoretical model. So, and what the main assumption for this theory?
Excuse me?
What the main assumption for your theory? From what it's followed?
We're just using that the point A won't bounce, so that.
And please, excuse me, could you open slide with your theoretical formula?
That formula, excuse me. This, if you give me the marker.
Yes, of course.
As you can see, this formula is literally based on this one. And if you look at the graph above, the theoretical values were for a free-falling chain that wasn't falling on a raised surface. So as it fell through the sensors, when the last rod went through the both sensors, the first bar didn't yet touch the ground. Understand what I mean? If we have a chain like this, and the sensors are here, the ground will be somewhere here.
So, and you, am I right? So,
Understand what I want to say?
not exactly, because where the so that's the surface, am I right?
Yes.
Yes, and this and here
These are the laser gates.
and here you fix
They are fixed to the wall.
Okay, so and where the reason between this and this? Where the difference? So
It will be the same. As we show in the graph above, we can see, that's why we use this graph at all. We can see that the 5-degree chain, 15-degree chain, 20-degree chain, any chain of any angle that we constructed has the same values. That just shows that they are same constructed and have the same characteristics for the free fall. This is a free fall graph. It isn't for the raised surface.
okay. So yeah, I got you. And how the angle between horizontal line and stick will influence on this effect?
The moment, how long the impact lasts will be longer, so the effect, the higher acceleration than g, will be longer in that period.
Am I right? Then, in order to increase the effect, we have to take sticks with a higher angle.
As I explained in the discussion, we tested this for the real sticks, and in the real sticks there will be some elastic forces. So we tested the for lower angles that are like this. If we have an angle like this, for example, as we shown, 45 degrees or something, the bounce won't be the same as this. For this, we would just have literally this, maybe it will have some elasticity. For this, we would more have this point literally pointing into the surface itself, and sometimes it will go like this, it will go like this.
So, can you show it in your experiment? Because I can believe that in this case, stick will go in this direction.
No, I didn't say it will go in this direction. I said it would bounce on the impact itself. because of the forces. If we have a stick like this, we have the mg, and we have this force, and we do this. We have this force which would rotate it, and this one that acts like this. And because of that, we have a bigger force on the point here itself, and that would cause the bounce itself. While here, the force that is acting on this point here is much less than the force that is rotating.
Okay, yeah, I got you. And how your theoretical model involve it?
As I previously said, we didn't have a theoretical model which would explain for the ray surfaces. That was just explaining how we think the phenomenon works.
Okay, so I got you, and let's take a closer look to this in the qualitative level. So you said that we have an additional acceleration, yes?
Yes.
And it means that if we increase the angle, the time of the acting of this additional acceleration will be more, yes?
Okay.
However, let's consider the slide number 4 again, please. Let's consider a normal force. Do you agree with me that the rotation happens as a result of the acting momentum of the yes, and in this case, if we have a high angle, the arm of this force is less than in this case. So
Can you explain it again, please?
So in this case, the arm of the normal force is the less than in this case. So it means that it's it's equal. So and how you can explain that?
Because we're here talking about just one rod, and in the experiment we have 15 rods, as I previously mentioned. Also, these two.
Excuse me, could you just maybe just move to the.
Okay, sorry. And these two impacts aren't the same at all as we just discussed.
I mean, so.
As we discussed, we just can compare for the two bigger angles like this.
Can't?
I mean, we can, but the thing we did was with lower angles, because we looked at the collisions that would go like this, pretty much. Not that would, not for the higher angles like this. And just the collisions are the same.
So, there, in theory, is it different or not?
It is different.
And where will be more? We will have left to.
Okay, we're out of time, sorry.
And thank you for the discussion. I want to clear some points. So we discussed a few questions, and in my opinion, the main question of this problem is the qualitative explanation, how it actually works. And I suppose we improved the qualitative explanation. And then I have a few questions about parametrical optimization, like what will happen if we increase the angle. So how I suppose that I hope that the future theory of the reporter will involve and included. And then also what will happen if the angle, if this angle will be equal to the 90 degrees, and
Okay.
also
Time's up, thank you.
thank you for.
Okay, we now have.
Thank you for the discussion between the reporter and students. So I have some questions for the reporter. First, do you think that the air drag will affect the quality of the
Airbrake. Yes, it affects the theory.
so do you think that you agree with the reporter that
I think that with increasing of the number of the rod, the air drag force will increase.
So for the second question, that you said that when the angle, the incline angle gets bigger, so the channel will flow faster, right?
As we said, that's in the range of the parameters that we tested, yes. But as we had the discussion, for some bigger angles, we don't know what will happen, and we speculate that at one point the chain will start.
So what is the limitation?
We haven't found the limitation.
Okay, so what do the opponent think is the limitation?
Of the number.
Oh no, when the angle is bigger, it will not fall faster.
If I remember, about 55 degrees.
55 degrees. Okay, thank you. So for the reporter, do you estimate the normal force?
Excuse me?
The normal force when it bounces to the surface.
As I mentioned, we just in our theory, in our phenomena explanation, we estimated that all of the collisions were classic.
Okay, so do you think that the falling acceleration of each stick will be the same or not?
Can you explain that, please?
The falling acceleration for each stick.
No, it won't, because they hit the ground at different speeds.
Okay, so hold on. What do you think that?
Acceleration for the H of T?
Each of sticks when it's falling down, will it be the same?
No, I suppose no.
Okay, so next question is for the reporter. Do you have the equation of motion to describe your motion of the
As you previously mentioned, we don't have. We only have the equation of motion for the free fall motion.
Okay, so next question for you that when you change the incline angle, do you fix the total length of their chain or do you fix the distance?
The chains were constructed so the distance between the central masses of the rods was consistent.
Okay, so the one agree with the reporter. He said that when he changed the incline angle, he just fixed the distance between the sticks and sticks, not the total length. Do you agree with him?
It comes to the same thing because remember.
Okay. Okay, so for the next question, the opponent just mentioned about the bounce of the sticks to the surface will affect, right? So how do you think it will affect this result?
I think that kind of the interaction will influence. However, I can't say myself.
Okay, so how do you think you can improve that if you calculate the bouncing in your experiment? Do you think it will more fix the theory?
I really don't know.
Okay. I think that's enough. Thank you.
In the case of the bouncing, the velocity of this point will be a little bit more.
Okay, thank you. Okay, so good morning, your judges and the opponent reporter. I'm the reviewer from Taiwan. Today I'm going to review problem number 6, that is chain. So this is the problem statement. It mainly talks about we compare with the free path, we construct a train with an incline angle, and we compare with the free fall. We have to investigate the phenomenon and with the relevant parameters, how will it affect the motion. So simply we can know that when the chain has an incline angle, the acceleration of the chain will goes up, so it will fall faster than the free fall. So this is the outline for the reporter. First, he says an observation of the graph that he compared with the fall and the free fall, and we think he should show the video, then we can clearly see it. And for his theory, he told us also about the rotating center using the Newtonian mechanism, and he mainly mentioned about the normal force, and he has a very clear qualitative explanation, but however, he has no equations, and he didn't mention about the angle in his theory. And about the experiment, he has the incline angle that's only for three kinds of angle, and he also changed the surface that he hits to the ground, and he has the numbers, the mass, the stiffness of the chain. And he has a beautiful setup, and he fixed the distance between the center of the mass when it is changing the angle. And the elasticity, but his concept that the elasticity of the string should analyze the acceleration and motion of, and he should analyze also the motion of the chain. And for his conclusion, he said that if the angle inclines bigger, the speed of the whole chain will fall faster, and the surface will matters. So this is the discussion between the opponent and the reporter. They first discussed about how will the normal force will apply on the center of the mass, and how will the chain be slower, and how about it will affect on the B point. That means it at the center of the sticks. And the reporter is agree with the opponent because he's listening to the opponent's explanation. And what the reviewer thinks that they should mention about the linear motion and the rotational motion, because when the normal force is doing on the B point, and we also should consider the velocity of the linear motion and rotational motion, which will also increase the velocity of the whole chain. So the rotational is very important because the B point will also rotating down. And for the second point, they talked about, well, the point A bounce up, and the opponent asked this, and the reporter said that they assume it won't jump off. And what the reviewer thinks that if it jumps out, apparently the rotating center will slightly or rapidly change, and the torque will be different from his theory that he mentioned about. And they also discussed about if the velocity is the same and as the free fall or not, and the graph is. For his graph in his experiment, he changed the angle, and the angle is all like free fall. And the point is, the reviewer thinks that first he should consider about the air drag, because we know that like the bird flying in the V shape, we know that for the first bird he will get the most of the air drag, like, and it will benefit the birds in the back to fly faster. So I think that the bottom of the sticks will have the most of the air drag. And he also should estimate about the normal force on the chain, and also the bouncing. He should calculate it in his theory, because I think it is matter, because it will affect the rotating center. Because the rotating center is also changing, and it will affect the normal force torque. And for our conclusion is that if the angle incline, the time will be slower, and the best angle opponent mentioned is about 55 degrees. And this is all my presentation. Thank you.
Now, to summarize the presentation itself, I would like to thank the opponent and the reviewer for an interesting discussion and the points they have made. Yes, I completely agree with them considering the theory model. We haven't really gone far into the theory itself. We stuck to the experiments. I would like if we would have discussed a little more about experiments and a little less theory with the opponent itself. We have demonstrated the phenomenon itself as it can be seen by the graphs. And we have tested some of the parameters. We said that there are more parameters that can be tested, like the length of the rods themselves. And I would end the summary like that.
Okay, questions of all three participants? Up to the front. Theory questions?
No. Question to the reviewer. You mentioned the drag force, the resistance force by the air, yeah? Am I right? You mentioned that the drag force from the air resistance should be included.
Yes.
What about the free fall?
Free fall?
Free fall, is it free fall?
I think it will.
So if we take into account the drag resistance force, will it be the free fall of the chip?
Yes, I think it should also be considered.
The opponent asked about the role of the trees and the strings in this problem. Differs with the free fall. What is your suggestion and theoretical model? How it affects if you want to put as a parameter in this model?
Of the thread? Yeah, got you. So during the collision, there is a transfer of the momentum, and if the thread is not elastic or is not absolutely elastic, we can observe a deviation, distribution of the.
And the review the role of the threads and the strings.
The strings?
Yes, and the speed and as a, in this model, how does it change? If you want to
How would the
put in
elasticity of the
theoretical
string
model.
change the model?
Yes.
How will the
If the strings stretch, how will that change?
because we know that when you force down for a long distance of the string, like because this is the short distance, this is the long distance, it will curve
Okay.
and it will strain. So I think it will.
Okay. Could you please put up slides like 14 or something? Yeah, yeah. One of the. It's one of your.
For which presentation? For our presentation.
Your presentation, yeah. Sorry, it was one of the ones where you had your you had changed the surface, for example.
Yes.
I'm just interested how were those averages? The points that you plotted on the graph, the one that was up in the top corner, were they averages of a number of tests, or were they individual tests?
Can you explain, because I didn't understand. The zoomed in graph.
Yeah.
It's just the zoomed in section of the graph itself, so we can, because on the graph itself we can see the value.
But were they averages?
Yes, they were averages.
Okay, what was the spread? Like how big was
the spread was actually very little because we used string which wouldn't, which had, which was, I wouldn't say unstretchable, but had low elongation properties.
So
you mean
is there any real So like for example, is there any real difference between the wood and the sponge?
as we said, we can see some difference, but we didn't get conclusive results for the role of the premise. We can just
the stick is horizontal and inclined, and they are all on the same
on the same surface.
Time is the same speed.
No, the one with the parallel sticks won't show the effect.
Yeah, because when we discussed, they told us that the time is same if the.
Yes, the time is same for these sticks if we consider the free fall, but if we consider on the surface,
same or different.
it will be the different if we have this. It will have different, but we can compare the one with the parallels to the free fall because there shouldn't be an effect. So we wanted to test the zero angle, but the problem is we can never construct the perfect zero angle. So we would have some inclines, and that wouldn't give us conclusive results.
I'd like to clarify your opinion both and probably the review.
You need to be quick, we don't have much time.
Okay, okay. not to use time.
Okay. Forms are filled in correctly, and I've checked them all, and mine's been checked as well, so we all know we're doing good. So we'll start with the marks for the reporter, so I'll read them out from going along. 4, 4, 6, 3, 4. Marks for the opponent. 6, 6, 7, 5, 8. And for the reviewer, 8, 7, 7, 7, 7. All right. Thank you. All right. feedback. So we there were a bunch of fours for the report, but there was a 3 and a 6. So Dina, do you want to
Yes.
for the report?
Theoretical model was not so complicated. It was not so complete, and then several parameters should be affected, but it wasn't mentioned, and some of them was ignored. And there was no comparison efficiency between theoretical model and the experimental model. And so according to the protocol, I gave 1 and 1 plus 1, totally 3 points. Yes.
Okay. And there was the 6.
I think I may do some vision works and do investigative analysis, surface angle, and something like that. And got some result. So I did 2.5 and 2.5.
For the opponents, we had a 5 and an 8. So now Dina.
Yes. 5, I suppose it is some measurements is not so different between 5 and 6, but it was some unclear points should be discussed during the discussion between opponent and reporter, but it was granted. So protocol was 1 point 5 in 2 parts and 1.5 plus 1, totally 5 points.
And Vladimir?
Okay, so as far as I understand from the discussion and from the opposition itself, the opponent grasped all main weak and strong points of the report, and I agree with that, and I slightly differentiate between the opponent and the reviewers of marks. They're quite consistent with their vision because of this question about air drag force, which I asked you. That's why I downgrade a little bit to the review, because it's not a free fall if you have drag.
I just make I think one thing I just want to make a comment about between the discussion that happened there. I think, reporter, I think you actually owe the opponent quite a bit, because he actually brought out a lot more of your understanding came out in the actual discussion than it did in the report, which actually brought, for me at least, your grade up quite a way. So I thought that was well done. You brought out a lot more understanding of that problem. The marks for the reviewer were fairly consistent. There was a single 8, which was me. I thought that was very well done. I summed up the grades. I was set on 7.5, and I've given a few 7s for reviewing already, and I thought that was better. So, other than that. Okay. So.